Okay, so today we get to venture into a new area. So we're talking about interacting molecules. In this case, we're going to focus on interacting monatomic gases to make our lives a bit simpler. So we have some symmetry, we don't have any internal stuff going on. The partition function for a single particle is relatively straightforward. Now once you start introducing sort of polyatomic compounds, then you have sort of asymmetry, and that makes things a bit more complicated. So in general, we're going to focus today on monatomic systems. So what we know from before is that the energy of microstate I for a monatomic particle, and this is something we've talked about extensively, is given by this expression. Essentially, we can think of this as having velocity in the x, y, and z direction. That is the only way that a monatomic particle can store energy if we neglect basically electronic and nuclear energy states. Whereas at high temperature, we should be expecting to see those modes being activated. But at reasonable temperatures, ideal monatomic gases are pretty straightforward. So what we've done is we take this and we calculate a single particle partition function. We take that and we calculate the partition function for a collection of particles. And this is something that we've done, and vector. We've done extensively for the past couple of weeks. That's a generalized approach that we've been taking for non-interacting systems. Now today, we're complicating it extensively. So what we can say is that the total energy of a microstate of collection of particles is simply going to be equal to the summation over all of the individual particles and their respective individual energies. In this case here, I is the microstate, and J is particle. This is very slightly different than what we had done before, right? Remember before when we were calculating the energy, we did it based on summing up all of the possible configurations. So in this case, we're just grabbing a particular exact snapshot. So if we know the velocities of every single particle in the system, we just basically take that information, figure out what its energy of every individual particle is, add up the energy of all the particles, and we have the total energy of the system. Right? This is distinct from what we've done before where we actually sum up all the states. Right? That's what the partition function is defined as. So, for an ideal non-interacting system, this is effectively the way that we're viewing the energy. It's just the energy of all the particles added together. But if you have interactions, we can't take this simplified of an approach. So what we're going to do is we're going to define some additional function. That is a function of the positions of all of the particles. Right, it says Rj is the position of particle J, which you can think of it as an x, y, z coordinates, or you can think of it as a radius, arm length, and two angles. Whatever the case is, this is a position vector. It just says where is the particle. So, what we need to do now with interacting particles is not only do the individual particles have energy, but the configuration of the system also has an energy associated with it. right? There's always some extent of electrostatic attraction or electrostatic repulsion between two different particles. So in this case, the energy of some microstate I for a collection of particles is going to be equal to the summation of the energy of every individual particle with its individual properties plus the energy associated with all of the positions. Now this U is some arbitrarily complex, some calculation or some function that we can't calculate right now. But we're going to use it as a stand-in and then find ways to simplify it so how we can try and actually calculate what this configuration energy is. So when we take this approach and we calculate the partition function, we have an indistinguishability factor. Let's put indistinguishable factor. That's right. It all out. This one here is the non-interacting contribution. So basically the single particle partition function. And we have some additional term here. I'm going to walk us through what this function is in just a moment. We are going to call this big function here z, which is the configuration integral. Sorry, I missed divided by kBt. Sorry. Okay, so the first two terms, the indistinguishability factor, the non-interacting single particle partition function, hopefully that looks very familiar. So the configuration integral, what we are doing in the configuration integral is we are integrating over all of the possible positions for every single molecule and for every single possible configuration, right? That's what this term right here is, the integral over the volume, and I did the dot, because there's lots and lots and lots of integrals. There's one integral for every single particle. So what the configuration integral says is that the partition function is every possible configuration of the system. And then we take every possible configuration of the system, scale the energy of that configuration by a Boltzmann factor, and then add it all together. So the integral is the adding it all together. We're assuming in this formulation here that the distance between configurations is so small that we can approximate as a continuous function. Then we're calculating for every single configuration what is the energy due to the intermolecular configuration of the system. We are scaling it by the Boltzmann factor, and then these dr terms right here are just, we are integrating over all the positions. Right, and this is a vector format as well. So for every one of these volume integrals, you would also have to break it down to dx, dy, dz, and you'd have to do that for n particles. So effectively you have three times n integrals to consider here. Not particularly very fun. This additional term that we added here, this v to the minus n, if we take u, I'm just going to put of Rn, as equal to 0, then z, the configuration integral, will just equal to the volume to the nth power. Now the reason for that, because if we just integrate over volume, you just get the volume as the answer. Right? E to the 0 is 1. If you integrate, so e to the 0 is equal to 1. Therefore, if you integrate over the volume dr, that gives you just the volume. So this v to the minus n is there as a correction term for when you don't have any interactions in the system. Are there any questions on the configuration integral? It seems very complex, but when you kind of step it down into individual parts, hopefully it makes sense. Right? So in the partition function, we have to capture every configuration of the system. Mathematically, that's how we do it. We have to move every particle to every possible configuration in every other system. Yes, question?
So the different integrals are behind each other, or you are integral within the integral of the rest of the integrals?
Right. It is the integral with the rest of the integrals. So for example, if we have a system of, let's say, 1, 2, 3 particles, what we have to do is we have to move particle 1 to every possible configuration of the system while keeping particles 1 and 2 and 3 constant. Then we also have to repeat and move particle 2 to every single possible configuration while holding positions 1 and 3 constant, and move particle 3 to every other possible configuration. So ultimately, at the end of calculating the configuration integral, you will have a result where every particle is in every configuration with every other particle in every other configuration. That's what we have to do in StatMech to give ourselves a statistical average of the system. Remember the ergodic principle? We can either calculate it in the time domain or the statistical domain. So if you were to let this system run out for infinite time, right, which is exactly what we're doing in thermodynamics for our calculations, you would eventually have sampled all the possible configurations of the system, because infinite time is an infinite time. And in that scenario, all of the particles would have been in all of the situations, and all of the other particles would have been in all of the other ones. But we're not going to calculate the configuration integral. We're going to simplify it down the best we can. So, in the canonical partition function, which is what we're working in, the Helmholtz energy is the most directly related to the partition function. Using classical thermo, we know that the pressure is related to the Helmholtz energy, by minus dA dV. So how does the Helmholtz energy change with respect to changes in volume? That gives us the pressure. So that tells us that the pressure for an interacting system is actually related to the configuration integral, not the single particle partition function. And that is because this v to the n cancels with the v to the minus n in our formulation. So that means every volume term is contained within the configuration integral itself. So in the case that you have no interactions, your configuration integral is equal to the volume to the nth power, and it'll just spit out the ideal gas law, exactly like we've done with the monatomic gas. Okay, is everyone with me? Okay. So what we're going to do is we're going to take this example here of 3 individual particles, and we're going to add up what we think the configuration energy could be. So we're going to approximate the configuration integral only considering that energy between two particles is the only additive energy that goes on in the system. So we'll write this out for three particles. So for three particles, we have U, R1, position of 1, U, position of 2, and U, position of 3. Right? The configuration integral for one particular microstate is going to be a function of just the positions of three particles. So if we approximate this as adding up the energies of pairs of interactions, we can get a function that would look like this. And in this case here, R12 is the distance between particle 1 and particle 2, which I think this is maybe algebra 2 or pre-calculus or something like that. You guys remember the distance formula? So the total energy of the system is given by three binary interactions and a correction term. So what we're going to be doing in this assumption here is we are going to be saying that this is approximately equal to 0. And I would say the foundation of about 95% of all molecular interaction studies make this assumption. But I do not necessarily think it's a very valid assumption. One of the criticisms of simulations is that you can kind of you can make it do whatever you want it to do. Try enough configurations, you can get the molecules to wiggle around and show you what you want to show. So in our research in our group, we spent a lot of time actually measuring the experimental properties on the molecular scale, trying to validate simulations. So that's one of the main areas we do in our research group. Okay, so if we were to draw this out visually, we have some 3D XYZ axis. We would have a position. Let me choose a different color. That would be position vector R1. You could have some position vector for particle 2. And this would be R1, 2, at the distance between the two of them. Now with the vertical lines on either side, remember that's a magnitude. But this could also be a vector as well. Right? You could have a potential energy function that is dependent on the angle that the two particles are interacting as well, which would be necessary for something that's asymmetric. So if we were to look at the collection of three particles, 1, 2, and 3. In between them, we would basically be looking at what is the energy stored in the configuration or the separation distance between particles 1 and 3, between 1 and 2, and the energy between 2 and 3. So in this case, not only do the particles have velocities and their own internal energy, but there's also an energy associated with the separation distance between each of the individual particles. So the total energy for this configuration would be energy 1, 3 plus energy 1, 2 plus energy 2, 3. Yes?
What's the physical meaning of the correction? So I mean the correction.
Oh, okay. So, what we're doing here is that we are first assuming that we can take the energy of just binary pairs. Because in theory, right, the real configuration integral is all of the particle positions all matter. But in reality, two particles that are very far apart, they don't know each other's presence. So you should expect that that energy of interaction is going to be 0. So instead what we're going to say is, let's model the configuration integral. Right? This is a model, binary interaction model. We're saying that instead of considering all of the positions of all the particles for every single different orientation, we're just going to say, you know what, let's simplify it by adding up individual pairs of interactions. And then if that's not accurate, right, we're having some other magical function that just corrects it. And then we're just going to say, we're going to neglect that function that corrects it. We're going to say that our model is pretty good, and we're going to focus on the binary interactions. Now, not all calculations neglect the multi-body term. Most of them will stop at 3-body interactions. I'm not sure of very much work that involves more than 3-body interactions. But in general, that's really kind of you stop it out. So, with this formulation of binary pairwise additivity, we can rewrite our big function here, right? Some unknown function that contains all of the energy of the configuration. And we're simplifying it. Make sure I get these limits right. As binary interactions. So these limits here of the summation are just so that we don't double count binary pairs. This term right here is a binary interaction parameter or binary interaction function. Or actually, more generally, that's the word I was looking for, potential. Binary interaction potential. With this assumption, then, we can calculate the configuration integral, which is NVT. That's the ensemble that we're working in. Same general form. The only difference here is that we have the product sum of all of the binary interactions, but it actually works out pretty well, because then when you take the logarithm of it, they all add up. But same idea. We're still integrating over all the possible configurations of the system, but in this case, now our function is much more simplified. Right? Our internal energy of the configuration is not related to all the particles added up, but just to the individual pairs of interactions. And so what we're doing is we're summing up all of the individual pairs of interactions. So let's look at our binary interaction potential, or interaction potential. Okay, as our separation distance, Rij, goes to infinity, what do we think that U should be equal to? 0. This is the ideal gas case. Right? In the ideal gas case, your density is so low that every particle is so far away from every other particle that it just doesn't feel its presence. Or you can also get the ideal gas scenario if your particles are so weakly interacting, even if they're near, they still don't communicate with one another through electrostatic interactions. So, if your separation distance goes to 0, what should our interaction be? Can we have a separation distance of 0 for two particles? No. So how can I mathematically say that we can't do that? Exactly. If the energy of two particles overlapping is infinite, that means it takes an infinite amount of energy to get them to stick on top of each other, which means it's never going to happen. So with this, let's take a look at some common examples of pair potentials. First one is the hard sphere. So if we plot it out, we have the separation distance, Rij, and the energy of that. That's it. That's the function. You can't see it here, but on the line it is just 0 until you hit some parameter sigma, which will relate it to the size of the particle itself, or the radius of the particle. And we can mathematically write out the function as a piecewise function. So effectively what this is saying is that we have two spheres. They don't interact with one another until they make contact, and then they cannot superimpose any further. There can be no overlap. Simple model, not 100% realistic, right? Because molecules and atoms are not billiard balls, right? There can be some overlap. You just have some strong electrostatic repulsion associated with electron clouds overlapping. But it is not to say that it's not impossible. One step up in complexity is the square well potential. So piecewise, if we write this one out, at very small separation distances below the radius of the particle, we're going to model it as a hard sphere repulsion. Basically, no overlap of particles whatsoever is allowed. At some intermediate separation distance, there is a slight attraction between the particles, and this is common. This is exactly what we see, right? Particles in general of a similar type will always tend to attract to one another. The length scale of this interaction is given by this parameter RSW, so R square well. And then above a certain separation distance, there is no interaction. So we get ourselves back to the ideal gas scenario at infinite separation. Now these potentials, the square well and the hard sphere, are nice potentials for analytical calculations. There's something easy that we can handle. If it's infinite, if it's zero, that makes the math a lot simpler. In between, it's not too bad. It's a constant value. So the hard sphere fluid, a square well fluid, these are models that can be used for simple systems. Or they can be used models that can use to look at scaling relationships or generalized understanding. But they're not going to be particularly, accurate for a real fluid or a complex fluid. Now for that, the most common potential that we use for a real or a complex system is called the Lennard-Jones potential. In this case specifically, I'm talking about the 612 Lennard-Jones potential. Who has heard of the 612 Lennard-Jones potential? Okay, a few people. Good. This is exceptionally common. I would say a vast, vast, vast majority of molecular level calculations use this potential. So instead, I'm going to plot U Rij divided by epsilon, which is one of the parameters, to make it easier. This is a continuous function. Given by that formula. Now this is a semi-empirical correlation. The second term here, this follows what theory would predict for what van der Waals attraction is. So the London dispersion forces are the van der Waals forces. They drop off as a function of r to the minus 6 power. So the further away you get, the less attraction that you have. But the problem is, as you get two particles closer and closer and closer together, that van der Waals attraction that corresponds to dipoles oscillating, right? So when you have a molecule, the electrons in that molecule are sloshing around, and they're sloshing around at a particular frequency based on the molecular configuration of that particular system. And a molecule that is exactly the same is going to have exactly the same frequency that those two things are going to slosh around. You're going to have slight electropositive and slight electronegative regions. And those frequencies are going to overlap such that the positive regions, the negative regions are slowly pulling these things together. And theory tells us that that attraction drops off at r to the minus 6 power. But as soon as two particles get close together, your electron clouds start overlapping, and then you have the Coulombic repulsion of the electron clouds and the negatively charged regions that is way, 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 way stronger than the sloshing around on a molecule size basis. And this is where we have the first term, and this is the electronic repulsion. So why 612? Well, 6 has a strong theoretical foundation. 12 is because it's 6 squared. That's it. For computational efficiency, It's way easy just to take the number you already calculated for the distance and just square it. Right, so the 612 Lennard-Jones potential has the -6 for the attraction and the -12 for the repulsion, just because it's numerically efficient to have the -12. And the general assumption then in the simulation community is that that's good enough. Right? For most of the time, the particles aren't going to get so close together that you have to worry too much about, well, are they repelling each other too quickly? But maybe if you're dealing with an exceptionally dense fluid, you might have to tweak those parameters a little bit. Okay, good so far? So, now what we need to do is take these binary interaction potentials, put them into our configuration integral calculation, and see if we can come up with a model. So we're not going to go through all of the nitty-gritty details, but if we were to take binary interaction parameters, make some approximations and simplifications. Essentially what we're doing is we're going to approximate this, all the way back here. We're going to be approximating this big nasty function and then simplifying it down. And if we do that, we can show that the configuration integral is approximately equal to, if we neglect sort of higher order correction terms in our approximation, right? So in this approximation, we're still assuming binary additivity, but we're not even very rigorously calculating all of the binary interaction additivity. We're still approximating that even further. But eventually, we can demonstrate that we can rewrite it as a relatively straightforward function where this beta parameter, is given by this function. The 4 pi rij squared, this is going from Cartesian to polar and symmetric. So what this is saying is that if we assume a particular binary interaction parameter, if we integrate that from 0 to infinity, following this function here, we can get an assessment of what the configuration energy or configuration integral is. But this is, of course, an assumption or approximation on an approximation on an approximation. But following this strategy here is where we can derive a very popular, or not very popular, but a very well-studied equation of state. We know that the pressure is related to the configuration integral. We now have a relatively straightforward function. So if we calculate the natural log of z, the configuration integral, getting ourselves ready to calculate the pressure, we get the Virial equation of state. And the virial coefficient, in this case we call it the second virial coefficient. This is because we're neglecting higher order approximation terms when we're trying to calculate the configuration integral, assuming pairwise additivity. So you can have higher order virial coefficients for a more accurate virial equation of state model, but that simply changes how we approximate the configuration integral. Yes? On the last equation is beta 1, yes. So we have the beta 1 in the configuration integral, and then when we put it through the derivation to calculate the pressure here, I rewrote it in the common way that we see the virial equation of state with the second virial coefficient, which is related to 1/2, negative 1/2, beta 1, which is this expression up here. So instead of rewriting it. Yes?
For the AB, T over B on the bottom, the last step should be B squared on the bottom?
Yes. This, this, you're talking about this V here?
Yes.
No, that should be, because I pulled it out into this term here. So if we were to redistribute, you'd have the 1 over V and then the 1 over V squared. Hold on, maybe I wrote. No, I have a mistake here. Where is my mistake? Ln 1 over V. Yeah, sorry, this is my mistake. That and that should go away. Because I've already I pulled them out in the first term. I got to correct that on my notes. Okay, so we can calculate the second virial coefficient based on the expression that we have now, assuming a particular pair potential. So let's walk through that for the simple system. So for a hard sphere, we have our interaction. I'm going to drop the ij for this distance. Is infinity if your separation is less than the particle radius, or rather this sigma tunable parameter. We can loosely think of it as the particle radius. And it is nothing above a certain size. So then we're calculating the second virial coefficient. And I'm factoring in the 1/2 to the previous expression. So a couple things that changed, if I just go back really quickly. Right, this is a little bit different up top here. Right, so the 4 pi becomes the 2 pi because of the 1/2, and then I switched these two because of the negative. Oops. Then the only other thing is we're breaking the integral up into two integrals because it's a piecewise function. The first term goes from 0 to sigma, where we plug in the energy of infinity, so you get minus infinity. And the second one is going from sigma to infinity, where you get e to the 0. So this whole term here goes to 0, and this whole term here goes to 1. So if we crunch the numbers, we get an expression for our second virial coefficient for a hard sphere fluid. Yes. We can do the same thing for square well. Skipping over the math, of course. So the square well potential gives you a slight attractive pull from your second virial coefficient, but this is actually only sort of relevant or detectable when you're dealing with a low temperature fluid. So it's slightly attractive, but not too much. Okay, we will have to continue our interacting fluid discussion on Friday. So we'll wrap up a little bit left what I've got here, talking about binary interaction potentials. But then on Friday, we're going to talk more about how do we take the information of potentially, a mole's worth of atoms. How do we come up with a simple function that can describe the particle configuration of the system? And for that specifically, we'll be talking about a function called the radial distribution function. Who here has heard of the radial distribution function? Very few people. Okay, this is one of the most important functions that I think walking away from the class to know about with StatMech. Because every single simulation paper or any theoretical paper talking about molecular interactions will almost always include a figure of the radial distribution function. And it tells us everything we need to know about the configuration of the fluid itself. So it's a very, very important function. So conceptually, it's tricky to calculate, but conceptually it's not too hard to understand, and it'll be a very important concept to walk away from in class. So we'll talk about that on Friday after wrapping up the sort of math of the particle interactions. All right. Have a good one.